Okay, class. So, I'm gonna go up there. Zoom is not working with me here. So today we're going to finish 6.3 and start 7.1. Reminder, on Monday you'll have an exam. All right. It's in class. You have to come to class to take the exam. You cannot take it via Zoom. You have to be here in class to take the exam. Bring your laptop. You need your laptop. All right. You're going to need a camera built into the laptop. All right. Because we're going to use Honor Lock. And this thing is pissing me off today. Go away. All right. Now, I remember I said you have calculators on your phone. So I was like, why need a calculator? Well, you need a calculator. So I have to teach this class the same way all the other classes are taught. And if you have your phone on a test, you'll cheat. So you have to bring a scientific calculator. All right. It can't be a graphing calculator. It has to be a regular calculator. And you don't want just like a regular cheesy one. It has to be scientific because like you need to be able to figure out like what sine inverse of like 0.679 is. I have no idea what that is. You plug it into your calculator, it gives you a decimal, and you'll have to round it, right? So some problems in WebWorks, you need a scientific calculator to do that. Other than that, I don't think you need it for anything other than figuring out what sine or sine inverse of ugly numbers are, all right? Yeah, there we go, finally. So have any of y'all ever used Honor Lock? Okay, yeah, it kind of sucks, right? Honor Lock is, it keeps you from going to other web pages, like during the web work exam. It does that, and I think it like videos you through the webcam, and like if you make any fast moves and it thinks you're cheating, it'll like flag you or something. It's just something they use for in-class online exams to prevent cheating, all right? There is information about it, like up here on the top in Blackboard, Honor Lock. I think under Start here, there's also some information. So read up on that. It's in here somewhere. Yeah, how to use Honor Lock. Okay, so there's information there. Basically, I think there'll be a password I'll give you at the beginning of class. You use that, and that allows you to get into the exam. And then you have to use the password again to submit the exam at the end of class. Something like that, okay? I have to figure out how to get it all set up. It's already giving me anxiety, making me make weird grunting and clicking noises without realizing it, bringing back my childhood tics. Honor Lock. Hopefully it'll work and it'll work fine. They just got the bugs worked out. So remember, there is the exam retry. Now, unfortunately, like the word retry here, we're not going to take like the best of your 2 grades. Typically, that's what retry would mean, right? It's not what it is in here. Remember, the retry, at best, you can get back half the points you missed on the exam, okay? And in order to take the retry, you have to do the corrections for the exam, and then you have to take them to the math gym and have the tutor there review it and then sign off on your corrections. And then you upload them in the Blackboard, I think, and then you get permission to take the exam retry, which then I guess is done outside of class on web work during this date. So it's just not an automatic, you get to just retry the test. They're making you like, you have to earn the chance to take the retry, okay? Anybody been to the math gym this week? I sent out the schedule for last week. I'm assuming this week's schedule is the same. I know they're still hiring tutors. The math gym has been in existence for like 20 days now, so they're still like developing it, right? But take advantage of the math gym, and you have the Tomas Rivera Center for tutoring. Make sure you get study groups, study with other people. Learning math is a lot easier when you're studying with other people, right? It's hard to do alone, okay? And don't forget that you also have over here, Tutor Me online tutoring. I think that's 24/7 done via Zoom. They have like an actual professor there to tutor you. All right. All right. So any other questions, administrative questions, any math questions? You can ask math questions in class. I will answer them. All right, well, let's try to finish 6.3 here. Where did we leave off? We're doing stuff like this. So here is an inverse trig function outside of a regular trig function. All right, well, remember cosine inverse always gave you an angle up here, whereas tangent and sine inverse always gave you angles over there. Remember our restricted domains, right? Remember how inverses work at all? Okay, well, let's think about cosine, right? Here's cosine, doodle 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 do. So cosine inverse tries to take, this is just a number, it tries to take that number and return it back to the angle it came from. So if I think of this as being that number, and I say, well, where did it come from? It could have come from there, it could have come from there, it could have come from here. There's an infinite number of choices. So cosine inverse, for it to be a function, one number in, one number has to come out. So we picked the one that was between 0 and pi, which would be the upper half of the unit circle for cosine, okay? So that was last Monday's lecture. Now, this happens to be a very special number, right? So one thing I could do, I could try to turn this into cosine, right? Because I know that sine of any angle is the same as cosine of 90 degrees minus that angle. So I could take this and turn it into cosine. That would be a cosine inverse of a cosine, right? But we don't have to do that here because this happens to be one of our special angles. We can just use the unit circle here. So negative 11 pi over 4. Here's a negative 8, 9, 10, 11. There's the angle negative 11 pi over 4. And so sine of this is just the y coordinate there. The y coordinate is negative root 2 over 2. So cosine inverse here, it doesn't see sine of blah, blah, blah. All it knows is negative root 2 over 2. These are the same number. There's just two different representations for the same number. Cosine has no idea that this number came from sine, right? That's just something we wrote, right? It just knows minus root 2 over 2. So it thinks, okay, what angle did this come from? Well, cosine is the x coordinate on the unit circle, right? So if I look at all the x coordinates with minus root 2 over 2, those are the possible angles. That cosine of those angles is minus root 2 over 2, but cosine inverse always gives us the one between 0 and pi. So it's going to give us 3 pi over 4. All right, so this one, because this is a pretty angle, we can just work it step by step, right? We find out what sine is. It's root 2 over 2 with the minus. And then we treat that like an x coordinate. We're doing cosine inverse, and we see, oh, it's that one. Now we could have done this trick. Let's do that trick instead. All right, we could say, I could say this is cosine inverse of, so I'm changing the sine into a cosine. So it's cosine of pi over 2 minus a negative 11 pi over 4. Okay, I want to add these, so I want a common denominator. If I multiply the top and the bottom by 2, I have that. Cosine inverse of cosine. So 2 pi and 11 pi is 13 pi over 4. Okay, they're the same thing, but I'm not going to get 13 pi over 4 back. Why? Because cosine inverse always gives me an angle between 0 and pi. This is not between 0 and pi, so I'm not going to get that angle back. So let's think about what it could be. Where's 13 pi over 4? Well, let's see. There's 8 pi over 4, 12, 13. There's 13 pi's over 4. All right. Cosine inverse is going to see that. Let's see, what is cosine 13 pi over 4 is negative root 2 over 2. Now we're in the same spot we were up here. It's going to look at this thing and say, this is an x coordinate, it's going to have to be this angle. Cosine of this is the same as cosine of that, but cosine inverse doesn't know about anything other than the top half of the circle. So it's going to say, it's got to be 3 pi over 4. So you can do it either way. I just do it this way because we can just evaluate this. I know that this is just minus pi over 2. I mean, minus root 2 over 2. Okay, so you can do it either way. All we're doing here is trig backwards and forwards and backwards and forwards. Now, we're going to do a whole bunch of examples like this where they put the inverse on the inside. All right. Okay, well, that's okay. Remember, the number we're plugging into a trig function, it's just a number. We interpret it as being an angle, right? And then it spits out some number that's between -1 and 1, right? Okay, but we think of that as being an angle. That means for the inverses, all right, for an inverse, we're plugging some number in, but we're thinking of what comes out as being an angle, right? If angles go into trig functions, angles come out of the inverse trig functions. This is just some angle. I don't know what cosine inverse of 4/5 is. I could plug it into a calculator and get some kind of decimal, and then I could plug that decimal into sine and it would spit out some kind of decimal, but that's not an exact answer. And the fact is I don't need a calculator to do this, right? This is just sine of some angle, where this angle is cosine inverse of 4/5. Okay, so all I did was call this theta. That's all I've done so far. Right? I don't care what cosine inverse of 4/5 is. I want to know what sine of that is. All right. So this is theta. We'll just call it theta for now. I don't care what it is. I want to know what sine of theta is. What is this? All right. Well, the angle here is this. Well, this tells me that cosine of whatever the angle is 4/5. This is an angle. What I know about it is that cosine of it is 4/5, but I need to know what sine of it is. Well, cosine is always adjacent over hypotenuse. So if I just draw a little triangle here, call this theta. I don't know what theta is. I just know that cosine of it is 4/5, and that's always the adjacent over the hypotenuse. Well, sine is always the how do I make a p? That's a 9. P. It's opposite over hypotenuse, right? Well, I know the adjacent over the hypotenuse. If I could figure out what the opposite side is, I could figure out what my sine is. So with this triangle here, I can be like, well, 4 squared plus p squared is the hypotenuse squared. So p squared is 25 minus 16 is 9. So p has to be either a positive or a -3. You might look at me and go, this is a triangle. You can't have a negative side, right? But wait, that question there didn't mention anything about triangles, did it? Right? It's just a math problem. This was just a trick we did. So technically sine here could either be, there's our opposite side and our hypotenuse is 5. So which is it? It can only be one of them. This is only one number. We can't be getting two numbers back. So let's think about it. Where is this angle? We know that the angle is cosine inverse of something. Cosine inverse always gives us an angle that's up there, right? By definition. Well, sine is always positive up there. Over here or over here, the y values are positive, right? So sine is always positive, so we want the positive version. That's how we know it's the positive version, okay? Okay, let's look at another example. I mean, we could do a bunch of examples. What if I put 7/9 here? What if I put 11/12? Whatever, no matter what number I put there. What if I just put the number 3, right? So if I just had a 3 here, what I would do is I would write that as a 3/1, so that way I would have an adjacent side and a hypotenuse, right? So if you ever look at it and it's just a number and you're like, oh, I don't know, right? Well, instead of doing like 300 examples where we have different numbers there, why don't we just do something like this? Sine of cosine inverse of whatever number, right? Well, I would call this sine of theta, where theta is cosine inverse of whatever that number is. That would mean that cosine of that angle is that number. So I'm doing the exact same steps I did, but instead of whatever it was, 7/9, I just wrote the letter x, right? So I would say, okay, cosine is adjacent over hypotenuse. I would call that x over 1. So the adjacent side is whatever number you gave me. Here's the hypotenuse. What is the opposite side? Because this is opposite over hypotenuse. Well, this tells me that x squared plus p squared is 1. So p would have to be positive negative square root of 1 minus whatever number you put here. All right, so this guy would have to be opposite over hypotenuse. Here's the opposite side. And the hypotenuse is just 1. So over 1. So instead of doing 300 different examples where I put 7/9, I put 6/5, whatever that number is, just treat it here as a number, right? Whatever that number is, you do the same steps, and boom, I have a formula. Well, which is it, the positive or the negative? Well, again, cosine inverse is always up there, and sine is always positive up there, so we know it's the positive one. So there, I just did every single possible problem you can have like that. Does that make sense? Right, remember when they used to have you like, they give you stuff like this, and they'd say solve for x, and then they give you a whole bunch of those, all different. So you had to learn how to factor and grouping and all this crap. And then they finally said, oh, here's the quadratic formula. It gives you the answer every time. And you're like, what? Why don't you just start off with that, right? Save you a lot of work. A lot of things we do in math classes, they run you through all these examples where it's the same thing over and over again with a different number. Just call that number x and do it like that, and then you have a formula for every single one of them, okay? So you could do that instead. And in fact, there's only several possibilities. You could have cosine of sine inverse. You could have sine of tangent inverse. There's, 6 variations, right? And each one of them is going to have a different little formula. That's in any math formula book. But in here, let's stick to numbers for a little while. Let's look at this guy. Cosine of tangent inverse. This is just some angle. This is cosine of theta. I don't know what tangent inverse of 5/12 is. I don't know, and I don't care. All right, I need to find cosine of this thing, and all I know about this thing is that tangent of it is 5/12. Okay. Well, let's see. Tangent is opposite over adjacent. I need my hypotenuse because cosine is adjacent over hypotenuse, right? So if I can get my hypotenuse, let's see, 5 squared is 25, 12 squared is 144. So square rooting both sides, square root of 169 is 13, I think. Okay. So which is it? Is it positive or negative? Well, let's see. Tangent, my angle is tangent inverse. Tangent inverse is always over there. Well, if we're looking for cosine, cosine is positive here and it's positive there because cosine is the x coordinate. So I know I need the positive version. So cosine is adjacent over hypotenuse. And it's the positive one because I know that my angle is on the right side of it. I know that this is on the right side of the circle, the unit circle. Cosine is positive over there. All right. Now we could have done cosine of tangent inverse of any number, right? How would we do that? Instead of doing a whole bunch of examples, how would I do this? I'd be like, okay, well, this is cosine of some angle where that angle is tangent inverse of x. So it tells me that tangent of that angle is x, right? That tells me since the angle is tangent inverse of something, it has to be over here. cosine's always positive over there. So I know it's the positive one. I draw my little triangle here. I'd be like, okay, theta. Tangent is opposite over adjacent. I could call this x over 1. Opposite over adjacent. What's h? Well, I know that h squared is 1 squared plus x squared. So therefore, h is positive negative square root of 1 plus x squared. So this guy has to be adjacent over hypotenuse. But we know we need the positive one because cosine is always positive over there. So there's your formula for every single problem they give you where they stuck a number there. This is always the answer, right? So I'll write that out. Cosine tangent inverse of any number is always 1 over the square root of 1 plus that number squared. So what if they gave you something else? What if they said x over 3? Okay, fine. X over 3, that's the answer. Right? You can plug in any expression you want. What if I wanted to have, instead of x, what if they had 2L plus m? All right, fine. Replace x with 2L plus m. You have a formula now. Does that make sense? Okay. That's just some added stuff I'm throwing in. Because they do throw some in like that. Let's look at this guy. This one just has a number here. But instead of cosine, it's sine now. It's sine instead of cosine. Okay, this is sine of some angle where that angle is tangent inverse of 7/4. And that tells me that tangent of that angle is 7/4. So let's see, tangent inverse always gives me something that's over here, but that's not enough, right? Because sine is positive here, but it's negative down there. So just this, I don't know. Well, we look at this, tangent of the angle is a positive number, right? Tangent of the angle is positive. Well, tangent is positive up here. Tangent is negative down here. So it can't be, it has to be up here in quadrant 1. This tells you it's the right half. This fact here tells you that it has to be up here. And sine is positive up there. So we know we need the positive version. All right, so if we do our little triangle trick, this is opposite over adjacent, so I'll say 7/4. I mean, I could have done this. I could have been like, this is 7/4 and this is 1. I could have done that. You'll get the same answer, right? But we don't want to deal with fractions. Let's go with a 7 and a 4, right? So what is our hypotenuse? Because this dude is it's opposite over hypotenuse. So we got the opposite side. The hypotenuse squared is 7 squared plus 4 squared. What is that, 65? So h is square root of 65. So opposite is 7, hypotenuse square root of 65. And we know we want the positive one because, again, sine is positive in that quadrant. And we know the angle's in that quadrant because tangent of the angle is positive, and it had to be on the right side of the circle. So those two pieces of information there helped us resolve whether it's positive or negative. Okay. And that's key for if we wanted to do a formula, right? So check this out, sine of tangent inverse. If I have sine of tangent inverse of some number, right? What is this? Well, this is x. That means this is a function of x. That means that this whole thing is a function of x, right? Like we have up here. X, function of x. So therefore, our answer should be a function of x, right? Let's do the same trick. Let's get us a formula for this. This is just sine of some angle where that angle is tangent inverse of x. That means that tangent of the angle is whatever that number is. All right. This guy tells us that the angle is over here. Okay. Whether it's in this quadrant or this quadrant, right, depends on if x is positive or negative. If x is positive, that means our angle's up here. If x is negative, that means our angle is down here. Because when we try to draw our triangle here, right, tangent is opposite over adjacent. We'll call this x over 1. So what's our hypotenuse? Hypotenuse squared is 1 squared plus x squared. So the hypotenuse is either a positive, negative square root of 1 plus x squared. So sine here is opposite over hypotenuse, square root of 1 plus x squared. So how do we resolve the sign here? Well, remember that x can be positive and negative. A lot of y'all, if you see this, you're like, that's a negative number. Wrong, right? X can be positive or negative. If x is negative, then this is a positive number. All right, so this guy right here could be positive or negative. So which one do we choose, right? We know this could be positive or negative. Do we need to flip-flop the sign or not? Well, remember what we just said over here. If x is negative, then the tangent would have to be up here. I mean, if x is positive, then tangent has to be up here. So if this is positive, we want this to be positive. So we don't want to flip the sign here, right? The positive or negative is built into our x there. If x is positive, this whole thing is positive. If x is positive, tangent has to be positive. That puts it in quadrant 1 where sine is positive. Okay? So there's your formula for this guy, right? Anytime you have sine of tangent inverse, this is always your answer. Whether x is positive or negative, you just plug it in. See, this guy right here, positive or negative, you square it, you get a positive number, right? So when you have things squared, it doesn't matter, right? Here, this could be a positive or a negative. So if they give you something like this guy, oh, not that one, do this one. Here's one where they actually have an x in there, but they put x over 3. So what? It's x over 3. They say that x has to be between -3 and 3. Well, we're looking at x over 3. You divide everything by 3. This is just a -1. This is positive 1. All they're saying is that the number they're plugging in is between -1 and 1. It has to be. If you plug in anything else, sine inverse chokes. It's only defined. This number here has to be between -1 and 1. That's the numbers that come out of sine. Those are the numbers that sine inverse can deal with, right? Okay, so that's all that they're saying right here is make sure that's defined. So we'll call this cosine of some angle, where that angle is sine inverse of whatever number over 3. So that means sine of our angle is whatever x over 3. Okay, fine. Sine is opposite over hypotenuse, right? So we'll call the opposite x and the hypotenuse 3. What is the adjacent side? We need to know because this is adjacent over hypotenuse. Well, adjacent side squared plus this squared plus that squared is equal to this squared. So that means that a has to be positive, negative, square root. 3 squared is 9. 9 minus x squared. So this guy is adjacent side over hypotenuse, but which one is it, the positive or the negative? Okay, well, what do we know? What do we know about this angle? We know it's sine inverse of something. Well, sine inverse always gives you something over here, and cosine is always positive over there. So we know it's the positive one. It doesn't matter what x is. Plug in any number you want. You can always test a number. If you're like, I don't know, try x equals 3. 3 over 3 is 1. What's sine inverse of 1? It would be pi over 2. What's cosine of pi over 2? 0. So test it out. So if I plug in 3 here, 9 minus 9 is 0. We get what we should. So just test out a number, right? If you plug this in, 3 over 3 is 1. Sine inverse of 1. Well, here is the y coordinate 1. So sine inverse of that would be pi over 2. Cosine of pi over 2 is the x coordinate there, which is 0. Right? So if I plug in a 3, I should get 0. Is this the right answer? Well, if I plug in a 3, I get 0. I just picked a test point that was an easy one for me to do in my head to check my work. We do that in algebra all the time. Students are like, I don't know if x times x plus y is x squared plus xy. They're like, I don't know. Well, pick a number. If I replace x with 1 and y with 2, are these equal? Well, 2 plus 1 is 3, and then 1 plus 2 is 3. Yeah, pick a number to test it out, right? I don't know if y'all ever did that when you were learning your algebra. If you're like not sure if you did it right or not, plug a number in for x or a or whatever it is and see if they're equal, then you know, right? You can do that here too. Pick a number, test it out. Let's look at this one. Okay, we have sine of tangent inverse of whatever. So this is sine of theta, where theta is tangent inverse of 4 times some number. So that means tangent of our angle is 4 times some number. It's tangent inverse, so that means our angle is over here. We're going to need more information. Sine here is positive up here, but negative down there. So we do need more information. So if we do our trick here, here's our angle. Tangent is opposite over adjacent. So I'll just call this 4x and call this 1. We need the hypotenuse because this is opposite over hypotenuse, right? I have the opposite. Okay, hypotenuse squared would be 1 squared plus 4x squared. So that means h is either positive, negative square root of 1 plus 16x squared. So this guy is opposite over hypotenuse. So which one is it? Well, again, with the tangent inverse on the inside like this, we have an x here. This x can be positive or negative, right? This x, you can plug in any number you want for x, right? As long as it's between here or here. So it could be negative, it could be positive, right? Pick a point. If you're uncertain, pick a negative number. If I plug in a minus 1/4, okay, that means my x here is negative. That means that this would be a negative number, all right? All right, so 4 times a minus 1/4 is minus 1. Tangent inverse of minus 1 is minus pi over 4, and sine of minus pi over 4 is in minus root 2 over 2. So if I plug in a negative number, I get a negative number. So if I plug in a negative number, that means this is a negative number, and sine should be a negative number. That means you want to get rid of those. So if I plug in a positive 1/4, I get 4 times a fourth, that's 1. Tangent inverse of 1 is pi over 4, and sine of pi over 4 is a positive root 2 over 2. It's a positive number. So if I plug in a positive number here, this whole thing's positive, and sine of all this should be positive. So just pick a test coordinate if you need to. Pick a test number. Pick one that's easy. This is the only number I know. I just know that tangent of pi over 4 is 1. That's pretty much the only tangent I know on the unit circle. I know where it's undefined, right? So I know that tangent inverse of 1 is pi over 4. And I also know I could swap the signs here. I know that one. Those are the only tangents I know. I know that because I graphed it so many times, right? What does the graph of tangent look like? At pi over 4, we always get 1. That was one of the key test points we used over and over and over again. That's why I remember that one. That's why I used that to test this out. The key here is that the tangent inverse, you're going to get an x by itself. It should be squared. All right. If it's squared minus or plus, you square it, that's gone away, right? But an x by itself, that could be positive or negative. So it turns out our sine, if it's up here, If x is up there, then our angle is up there, and sine should be positive up there. So if this is positive, and sine should be positive for up there. All right. If this is negative, all right, then tangent is negative, and tangent is negative down there, and sine should be negative down there. So that's how you know this guy has the sine built into it. Okay, that's it for this section. And now we are moving on to 7.1, which is a lot of fun. Fundamental identities. Boom. So what do we know about trig identities? An identity is where something is always equal to something else, right? We know the Pythagorean theorem. Yep, well, you knew that, right? But if you scaled it, x over r is cosine squared, y over r is sine squared, and r over r is 1. This was your first Pythagorean identity. Cosine squared plus sine squared is always 1, right? That's basically applying the Pythagorean theorem to a triangle of hypotenuse 1, okay? Or we could have scaled everything by x, right? Basically, we're saying, oh, no, make this side 1. See, x over x is 1, y over x is tangent, and then r over x is secant. So that was our second Pythagorean identity. Or we could have divided everything by y squared. X over y is cotangent, y over y is 1, and r over y is cosecant by our definition. So these were our three Pythagorean identities, okay? This one, we quite often use it like this. Cosine squared is 1 minus sine squared, or we do sine squared is 1 minus cosine squared. So this we use constantly. We usually use it in one of these forms to turn a cosine squared into a sine squared or vice versa, right? So these are going to use a lot. Other identities, okay, well, we know that tangent is always sine over cosine, right? We know that it's 1 over cotangent. And of course, we know that secant is 1 over cosine. And we know that cosecant is 1 over sine. Came straight from the definitions, right? So these were your quotient and reciprocal identities. We also knew this, trig of theta is always cotrig of 90 degrees minus theta. That was your cofunction identities, right? You could switch from one function to its cofunction if you switch from the angle to the other angle in the triangle. We had that identity. And I say identity, these are equal no matter what you plug in. We also had even odd identities. We know that cosine of negative theta is always just cosine theta, right? Remember, cosine looks like this. The right side looks just like the left side. And we knew that sine was odd. We knew that tangent was odd. And let's see, we know that secant is 1 over cosine. Cosine's even, so secant is even. Cosecant, since it's 1 over sine, and sine is odd, this dude's going to be odd. And cotangent, since cotangent's just 1 over tangent, and tangent's odd, cotangent has to be odd. So those are more identities. So we can use these identities to prove new identities. All right, so here we go. Identities, 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 identities. So if they give you something and you want to know if it's an identity, right? I mean, if you get something like this, like 1 over tangent equals cotangent, right? You might look at that and say, am I solving for theta, right? That's why I always put this. These are identically equal. That means the solutions to this equation are any real number where they're defined, where it's defined, okay? Can't divide by 0. As long as you're not dividing by 0, you can plug in any number you want. So if you graph this and you graph that, their graphs are the same graph because these are identically the same thing. So you can test for identities, you can test, is this something that all solutions are true, right? Here's cotangent. Oh, and it's also 1 over tangent. They're the same graph. These are the same thing, okay? Normally, if this was like that and you're asking for what are the solutions to this equation, this would be some kind of squiggle. This is some kind of squiggle, and you're looking to see where the squiggles cross. That's your solution, right? Well, here the squiggles are the same, exact same squiggles, okay? So that's what an identity means visually. So what if we have stuff like this where we want to be able to prove identities here, okay? So here's a real easy one. Verify that this is an identity. When you have something simple on one side and something complicated on the other, it's typically easy to start with one side, like the left-hand side. Tangent is sine over cosine, and then we have times cosine. Those cancel out, and we're left with just sine. So that's the right-hand side. So we just proved that's an identity, okay, by substituting, using identities that we already knew. Okay, we can do another one here, another real easy one. All right, here's a big pile of stuff. So I'm just going to try to simplify that until I get to the other side. So the left-hand side, cosecant is 1 over sine. And then I have a cosine here. And then tangent is sine over cosine. So I can see the cosines and the sines cancel. I'm just left with the number 1, the right-hand side. Right. You can always, that's one trick. You can always turn things into just sines and cosines. We don't need 3 different trig functions here. You can always reduce it to sines and cosines. This guy, now when you look through the book, they're going to show you how to do this step by step, which isn't very helpful. Because they're going to be like, and then you can do this, and then you can do this. But there's like a million things I could have done. How did you know to choose to do that one thing? So we need some motivation here. So like this guy, these are all sines, and that's a cosine squared. Well, I know that cosine squared plus sine squared is always 1, right? So I know that sine squared is always 1 minus cosine squared, or cosine squared is always 1 minus sine squared. I know that in the back of my head. So I'm not worried about having sines over here, even though there's cosines over there. I know I'm going to get a sine squared, and I can turn that into a cosine squared, right, via this. The other issue here is, well, the main motivation is samesies. That's what I call it, samesies. This is cosine of x. It's trig of x. This has trig of minus x. Well, let's get rid of that first, right? Trig of x, let's rewrite that as trig of just x. So the left-hand side, I got a 1 plus sine x. And this guy is an odd function, so I can pull that minus sign out. All right, so now I have trig of x instead of trig of minus x. There's no trig of minus x over here, so that's the first thing I'm going to resolve and making it look a little bit more the same. Now I can just multiply this out. 1 times 1 is 1. Positive sine x minus sine x, those cancel. And then I have a negative sine squared. But I need cosine. Well, that's fine because 1 minus sine squared is cosine squared. And that's the other side of the equation, okay? So the first motivation there was get rid of that because there are no negative x's over here. And then the rest of it just follows. You will use these constantly, those two right there. Let's look at this one. What's the motivation for our first step? When I look at this, I'm like, okay, this side's more complicated, so I'm just going to turn this into that maybe. Eventually, you'll have a big pile of stuff over here, so you'll want to work with both sides at the same time, okay? So here we're just going to do the left-hand side to the right-hand side. Who wants to deal with secant? Secant sucks. Secant is just what, 1 over cosine, right? So I'm going to replace secant with 1 over cosine. And I'm not freaking. I know I got to get it to sine squareds. These are all squared. As long as the cosines are all squared, I know I can turn them into sine squareds, right? Because cosine squared is always 1 minus sine squared because of the Pythagorean theorem. So that's okay. But the other thing is this is not a fraction. This is a fraction over a fraction. So let's not do that. Let's, instead of dividing by this fraction, I will multiply by its reciprocal. So if I distribute this, I will have cosine squared over cosine squared, and then minus cosine squared. This is just 1. And what do you know? 1 minus cosine squared is always sine squared. Sine squared, right? Sine squared is always 1 minus cosine squared. So 1 minus cosine squared is always sine squared. That's the other side. Does that make sense? Kinda? It's just step by step. What are our motivations? I mean, I could replace this with all kinds of different things, right? First thing, I got rid of secant because it sucks. I'm not worried about cosines because I can always turn cosines into sines as long as they're squared. All right, this guy, well, this side's more complicated. This is real simple, so I'm just going to do left-hand side. We don't need cotangents and cosecants. We can replace cotangent with cosine over sine, and I'll replace cosecant with 1 over sine. So again, this is not a fraction, this is. So instead of dividing by a fraction, I am going to multiply by its reciprocal. Those go away, and I'm left with cosine. You see how often we write sines and cosines and sines and cosines. That's why you use these, right? Unofficial sign notation, right? So for your scratch work, it'll save you time. Create an identity. All right, so in here they give you stuff and they say, prove this is an identity, or they ask you, is this an identity, right? Well, in like algebra class, I didn't just come up with like this long ass polynomial and say factor it. I wouldn't even know if it's factored or not, right? I would have started off with the factors, multiplied it out, and then give that to you and say, here, factor this, because I just reversed engineered it, right? So the best way for you to get good at these identities isn't by looking at some huge identity and spending all day trying to prove it, right? Start off with something simple and create your own problem like this. We have a 2 tangent theta secant theta. They want us to rewrite it strictly in terms of sine. Okay, we'll do that for them. But we could turn this into anything we want, right? I could say, okay, tangent is sine over cosine. Secant is 1 over cosine. So I have 2 sine. This is cosine squared. Cosine squared is always 1 minus sine squared. So 1 minus sine squared. Boom, I did what they wanted. I turned it all into sines, right? But I could have done all kinds of stuff. I could have said, this is the same thing. I could have added 1 and subtracted 1, right? And then I could have replaced the 1 with cosine squared plus sine squared. And I could have made it as complicated as I wanted and said, okay, this is an identity, prove it. One more problem here. This is where it gets fun. So here we're going to learn some motivation here. So this is a big pile of stuff. This isn't. All right, there is no minus thetas here. So obviously we can make samesies, right? The left-hand side. Let's just get rid of all the minuses. Sine is odd, so this minus sign can be pulled out, but there's 2 of them because it's squared. So if we pull out 2 minus signs, they're going to cancel. This minus comes along with this. These we can throw away because cosine is even. This minus sign will come out. This minus sign we could throw away. So I'm trying to turn this into that now. At least these are all trig of theta. Trig of theta, fine. This is a fraction, that isn't. So how am I going to get rid of this, make this not a fraction? I have to factor this and hopefully I can cancel that out. That's the goal. That's the only thing I could do. This is the difference of two squares. So it's sine minus cosine times sine plus cosine. Remember your difference of two squares, sine squared minus cosine squared. The minus cosine sign and the positive cosine sign cancel. What do we have on the bottom? We have a minus sine theta minus cosine theta. Well, I need this to go away. If I factor out the minuses here, I can make that go away. And if I bring that minus in up here, I'm going to have a minus minus cosine and then a minus sine, which is the right-hand side. So you follow the motivation. The book's just going to show you, and then you do this, and then you do this, and then you do this, and you're going to be like, yeah, well, I could have done a million things. Why did you do that? Right? We're keeping an eye on where we're trying to go, right? The samesies method, right? This is a fraction, this isn't. So how do we reduce a fraction? Well, we're going to have to factor that to make that go away. That's how you know to take this and factor it, right? Because that isn't a fraction. All right, that's it for today, folks. This guy, yeah, see, this is sine of negative theta times sine of negative theta, right? So if you pull out two minuses, they cancel. Yeah.